Most engineering students spend years learning formulas, and yet, when they face real problems, they feel lost. So, there might be some gap, and that gap is about understanding the system and thinking in system under uncertainty. Because engineering was never really about equations, it's about understanding systems. Today, we'll talk about the most important concept in engineering. What is a system? But before we start, this video is not about solving problem. It's about understanding how problems are structured. Because formulas don't exist their own. They describe behavior inside something larger. That larger thing is a system. You can think like a formula is a part of a big machine. So let's first define system. We can think a system as a collection of interacting component within a boundary that transform input into output under uncertainty. Let's simplify this again. We have one input and then process and then output. If you come from a computer background, it will be almost similar to how computer CPU work. But in system, in engineering, we have input, process, output, but we also have some other component that we need to consider. And I will be talking about them in the later video. Every engineered object follow this structure. Always, whatever you see in this world, whether it is a rocket or a car or type of, let's say, machine, it should follow all of these steps from input to process to output. But there is something different and it's important as well. And it is known as a boundary. So what's a boundary? This box represents the boundary. The boundary defines what you choose to study and what you ignore. For example, you are building a braking system, and inside the braking system of a motorbike, and inside this braking system, you are not going to study about rocket, because what you just need is the part or is the knowledge that makes the braking system efficient for a motorbike. You are not making a rocket, so that's a boundary. Engineering begins when you decide what belongs inside my model. Different engineers can choose different boundaries and both may be correct. Modeling starts here. The other one is internal interactions. Forces interact, energy transfer, signal propagate. This is where equations live. Equations are not the system, they describe relationship between the system. For example, when we see F equal to ma, we can get the force of a running bike on the tire well, I'm not that much good in drawing, so anyway, so you can calculate the force of a running bike with given mass, but it's just a part, the force is just a part that is exerting on the this downward, but the system would be the braking system, and this formula just describe a part of a braking system, not the whole braking system. So now let's take an example of braking. Let's zoom in inside this one and try to see where does input, process and output come inside braking system. So I will write here braking system and the input. So what can you think the inputs would be for a braking system? So if I get this, let me just copy it. where is, yeah, and let me just paste here. Okay, so if we consider this motorbike and the let me zoom in, yeah, this braking of a motorbike, so what are the inputs that you can think of? So the input is anything that you give yourself, or even that is a force, or even presses the pedal. So the inputs for the braking system would be the driver presses pedal. The other one can be the vehicle speed. What can you think else? So it can be the road, smoothness of road, because if the road is good, then it might take a bit more millisecond to stop when it is a rocky area. And what is the system? When you press the pedal, when the driver presses the pedal, and considering the vehicle speed and the smoothness of the road, the next part will be the system. And what the system represent? Hydraulic pressure, or the brake pads, or the friction interaction between the pedal, and what will likely be the outputs. So the output might be the expectation of a driver when they presses the pedal on the braking system. So for instance, what is the expectation? Speed decreased, heat generation, or let's say stopping distance. So these are the three things: input, system, output in a braking system. Now notice something. You may use, inside all of these, you may use F equal to ma, but as I told you earlier, this equation only describes one interaction. The braking system is much larger. Engineering means understanding the whole structure, not just inserting numbers into formula. And if you want to take another example of a engine, let's say we have an engine. What can be the inputs of an engine? So the input can be fuel, the air, the ignition timing, or let's say people are researching about using hydrogen as a fuel instead of the fuel like gases. And what will be likely the internal interactions? That can be combustion, pressure rise, mechanical motion, for example a motor, and thermal losses. Because this type of loss, I will tell you in the later video why this type of losses are expected. And what can be the outputs? Output can be torque, thrust, heat, or exhaust gases. Thermodynamic equations describe just one part, and that will be the combustion, but the engine is the system. If you want to take another example, let's say an example of a breeze. And this breeze, what are the inputs of a breeze? So take a pause and think about it. I hope you might have come up with something. So the inputs of a breeze, first of all, let's understand what is the main purpose of a breeze. The main objective of the breeze is to, or you can say, is to connect two roads. For example, vehicle loads and wind forces. The other one can be temperature variation in the cold, in the summer. And what are the internal interactions? It can be stress distribution, because if I will draw let's say a breeze, I know it's not perfect, but it will work. in our explanation. So this is a triangle based bridge, and the stress distribution among all these layers, and then the force transfer, material deformation, because of course if a heavy truck is going on the bridge, it will deform a bit. And what are the outputs? Output can be stability. What we expect that if the bridge is good and then a vehicle is passed from that bridge, it should not break the bridge. The other one can be deflection. A stress equation describe behavior. They don't define the system itself. And now you can see the bigger picture. When we describe about the braking system, we saw when we learn about F equal to ma, we just learn the forces. When we learn about thermodynamics, we just describe about combustion. When we learn about a stress equation, we just learn its behavior. Now the important part, why students struggle. Here is where many students struggle. Education often teaches equations separately. For example, in this three system, we never learn it together. We learn it separately. For hydraulic pressure, we learn separately brake radiation, we learn separately brake pad, we learn separately friction interaction. But real engineering problem don't arrive level. They don't tell you use equation number 3 or use equation number 4 or use Newton law of motion. You must first understand the system, only then do equations become useful. Now the key moment. Earlier in the video, you might have heard the word uncertainty. Let's now describe a bit what is uncertainty. So uncertainty is something that you don't have enough data. For example, the materials that you might be using vary, the measurements contain error, the environmental conditions change, human inputs fluctuate. In our braking system, a brake pad doesn't have one perfect friction value. In our bridge, loads on a bridge are never constant. Engineering is not designing in certainty, it is designing under uncertainty. Even though we don't know, but we still try to reduce as much as uncertainty as we can, and that is designing under uncertainty. Like everything in this world you see, whether it is the system, no system is absolute truth. There are flaws in every system. I will tell you one story. Until SpaceX built reusable rockets, we didn't have enough data. And then, when we didn't have enough data, people decided that reusable rockets are impossible. But Elon Musk team built reusable rocket. Reusable rockets are possible because we have enough data for making a reusable rocket. So in every system, there is nothing, no absolute truth. That people might believe impossible because we don't have enough data for that. Now, if we rebuild all of this together, and I told you there are some other component as well inside the system. So if we rebuild, we have input, outputs, boundary, internal interaction, constraints, uncertainty. These are the components, and when you start thinking this way, you will stop memorizing. You will start modeling reality. And modeling is what engineers actually do. If you understand systems, formulas become tool. But if you only memorize formula, you remain dependent on a structured problem. This channel explores engineering through first principle, understanding systems, assumption and uncertainty behind real world design. Welcome to Tech and Engineering.